In this video, we'll look at the fundamentals of probability, and we'll begin by just looking at some definitions and then work our way into some examples later on. So the probability of an event is the proportion of times that the event occurs in the long run, as a probability experiment is repeated over and over again. This goes hand in hand with the next idea, the law of large numbers, which says that as a probability experiment is repeated again and again, the proportion of times that a given event occurs will approach its true probability. Now, when we use these terms, law of large numbers, and we talk about probability in general, we are referring to a theoretical idea. When you flip a coin, anything can happen, and even if you flipped a coin maybe 10 times, you might not get 5 heads and 5 tails. But if I said to you, what's the probability of flipping a coin and getting heads, you would typically say, oh, that's 50%. Because in the long run, if you flipped a coin millions and millions of times, then the proportion of heads that you would get would be 50%, and the proportion of tails would be right around 50%. And so, again, in general, when we're talking about probability, we're referring to theoretical probability and the idea of the law of large numbers. Now, later on in this video, we will talk about empirical probability, but most of the time, when we refer to probability, it is on a theoretical level. Okay. Next term, sample space. A sample space contains all the possible outcomes of a probability experiment. So in that experiment where we were flipping a coin just now, the only possible outcomes were heads or tails. And so the sample space in that case would quite literally be just heads or tails. And then an event of interest is an outcome or a collection of outcomes from a sample space. So when I ask the question, what's the probability of getting heads when you flip a coin, or what's the probability of getting tails when you flip a coin, those are specific events that I'm referring to. Now we also have a probability model for a probability experiment consists of a sample space as well as a probability for each event. And some notation that we'll use, we'll say if A denotes an event, then the probability of the event A is denoted capital P of A. Okay, next idea is probably the most important one moving forward, and this one is called the fundamental probability principle. And this basically says that if a sample space has n equally likely outcomes and an event A has k outcomes, then the probability of event A is equal to the number of outcomes, the number of times that you would have event A divided by the total number of outcomes in the sample space. And so we'll refer back to this a number of times moving forward in this module. But the probability of an event occurring is the number of times that event occurs out of the total number of outcomes in the sample space. And when you calculate probabilities, they're always going to be between 0 and 1. You can't have a probability any lower than 0, and you can't have a probability any greater than 1. And so you can have probabilities of 0 and 1. 0 says you have no chance of that event happening, and 1 says you have certainty of that event happening. And it's also going to be important to characterize what we call unusual events in this class. And those are events where probabilities are small. Think of the empirical rule like we saw before, and anything that was more than a couple of standard deviations away from the mean, we deemed unusual. And it's pretty consistent in this definition with an unusual event of an unusual event now. And as I say here, most often any event whose probability is less than 0.05 is considered to be unusual. So 5% is going to be our cutoff. Anything that's lower than 5%, anything that has less than 5% probability, we will call unusual. Okay, so with that in mind, let's take a look at some examples. In this first one, we're just listing the sample space for each event. And so imagine rolling a die. When you roll a die, it's only got 6 sides to it, right? And so you can get numbers of 1, 2, 3, 4, 5, or 6. And so that's my sample space. Those are all of the possible outcomes when I roll a single die. Or as we just saw when I talked through some definitions earlier, when one coin is tossed, you could get heads or you could get tails. Now it starts to get a little bit more complicated when we start tossing 2 coins or 3 coins or 4 coins. But what I'm going to show you is if you can organize yourself by listing out the sample space, then it's going to make our lives a little bit easier. So if 2 coins are tossed, well, you could go heads, heads. You could go tails, tails, but you also might go heads, tails, or tails, heads. And so when you toss 2 coins, there's actually 4 outcomes you could see here in the sample space. 3 coins being tossed and 4 coins being tossed really steps up the level of complexity a little bit. So let me list things out over here. So here, let's say 3 coins, and we'll start listing out things in an organized way as much as possible. And then over here, we'll do 4 coins. Okay, so when we toss 3 coins, let's do the easy ones first. We could end up with heads, heads, heads. We could end up with tails, tails, tails. Or you could end up with heads once. So you could have heads, tails, tails. Or you could have tails, heads, tails. Or it could be tails, tails, heads. If you look here, you can see what I did is I basically took that heads that we had in here. We had heads one time, and I kind of distributed it through to the different places in these 3-letter arrangements. And now what I can do is I could say, okay, well, imagine if you didn't have heads one time, you could have tails one time. So I'm just going to replace HTT now with THH, and then I'll distribute the T through just like I did previously. So this becomes HTH and then HHT. And so we have a grand total of 1, 2, 3, 4, 5, 6, 7, 8 outcomes in this sample space. And that's actually something that I knew going into this example. I knew that I was going to have 8 outcomes because if I'm tossing 3 coins, there are 2 outcomes each time. For each outcome of the first toss, there are 2 outcomes of the second toss. And therefore, there would be 2 times 2 outcomes for the first 2 tosses, or 4. And then for each one of these outcomes of 2 coins being tossed, there are 2 outcomes for the third coin being tossed. So in other words, if you just did 2 times 2 times 2, you could think about this through what's called the multiplication principle of counting, and you could arrive at the number of items that you would have inside that sample space. So with 4 coins, if we use this idea, if we know that each time we toss a coin, there are 2 possible outcomes, and we can apply this multiplication principle of counting, then 2 times 2 times 2 times 2 suggests that we should end up with 16 in our list. So let's go ahead and list it out, and this will probably be the only time in the class that I'll list all of this out. And hopefully, I don't think that you'll need to be able to list this out, but if you do, just refer to these notes here, and that should help. So, okay, 4 coins being tossed. You could have heads, 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 heads. You could have tails, 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 tails. Now I'm going to list it out where you have heads once. And again, what I'm going to do is distribute the heads through here. So you could have heads, tails, 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 or you could have tails, heads, tails, 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 heads, tails, 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 heads. Okay. Now instead of having 1 heads and 3 tails, we could have it the other way around. So let me write tails, heads, 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 and then I'm going to distribute the tails through. So this becomes heads, tails, heads, heads, or heads, heads, tails, heads, or the last one being heads, 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 tails. Now at this point, this gives us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 things listed in our sample space. We know we have 6 more, and the other 6 are going to come from having 2 heads and 2 tails. So you could have heads, heads, tails, tails. And then what I'm going to do is I'm going to fix this first heads, and I'm going to distribute the other one through. So I could have heads, tails, heads, tails, or you could have heads, tails, tails, heads. And now what I'm going to do is I'm just going to switch all of the H's and T's with each other. So you could also have tails, tails, heads, heads, or you could have tails, heads, tails, heads, or you could have tails, what's my last one going to be? Tails, heads, heads, tails. There we go. So 16 possibilities. All right. Now, how about this one right here? List the sample space for the cards in a standard deck. Well, if I'm looking at a standard deck of cards, there are 52 cards in that deck. And later on, when we do go through an example in this module where we are working with the deck of cards, I'll give you a nice image to visualize that sample space. But you should know that we do have 52 possibilities in that sample space. Okay, now I want you to see, now that we have the sample spaces listed, how much easier some probability examples are. So if we take a look at this next question, find the probability of drawing a face card from a standard deck of 52 cards, we need to apply that fundamental probability principle. And we need to say, how many face cards do we have in a standard deck of 52 cards? And so that's the number of ways that our specific event can occur. And then we're going to divide that by 52 because we have 52 outcomes in our sample space. So the big question is, how many face cards do we have in a standard deck? Well, the face cards are the kings, the queens, and the jacks. Those are the cards that all have faces on them. There are 4 suits, and there's a king, queen, and jack for each suit. So we actually have a total of 12 face cards out of the 52 cards. And if you take 12 and divide it by 52 in your calculator, you get a decimal. You can convert that decimal to a percent if you'd like, and that way you can describe the probability either as a fraction, you could describe the probability as a decimal, or you could describe the probability as a percent. Now when I punch this into my calculator, 12 divided by 52 ends up giving me a decimal of approximately, use the wavy equal sign, it's approximately 0.23. So about 23% of the cards in a standard deck are face cards. And so the probability of drawing one card from a deck and getting a face card, it's about 23%. Example B, what's the probability of getting 3 consecutive tails when tossing a coin 3 times? So let's go to the case where we actually listed out all of the possibilities. And out of those 8 possibilities, how many of those involve getting 3 consecutive tails? Well, that would be 1 out of those 8. And again, you convert that to a decimal just by saying 1 divided by 8 in your calculator, and you'll get 0.125. So you have a probability of 12.5% of flipping a coin 3 times and getting all tails. Or what's the probability of getting 2 heads and 2 tails when tossing a coin 4 times? So you go to your list over here. It's nice and easy when you have that sample space listed out because you simply count the number of ways this event occurs, and then we divide by the total number of outcomes in the sample space. And remember, for this we said that there were 16 outcomes in the sample space. And so if we count how many times we can get 2 heads and 2 tails, that's 1, 2, 3, 4, 5, 6. So 6 out of 16, which is the same as 3/8, which is the same as 0.375 or 37.5%. So you have a 37.5% chance of flipping a coin 4 times and getting 2 heads and 2 tails. That's sometimes an example that confuses people a little bit because they often think that if you flip a coin 4 times, you should get 2 heads and 2 tails 50% of the time. But it doesn't work out like that. As you can see here, 37.5%. Okay, let's keep going. In this next one, it says a coin is again tossed 4 times. What is the probability that all 4 tosses have the same result? So another way of asking that question is saying, what's the probability of either getting all heads or all tails? Well, how many of the outcomes out of the 16 in the sample space are either all heads or all tails? Well, for this first one, it would simply be 2 out of those 16. 2 out of 16 is 1 out of 8. As we saw up above, 1 out of 8 is about 12.5%. So you have a 12.5% chance of flipping a coin 4 times and having all 4 tosses having the same result. And then for this one, what is the probability exactly one of the 4 tosses is tails? I'd go back to my list and let's count how many of the outcomes in the sample space have exactly one of the 4 tosses being tails. And so let's see here, we can go to, it's these outcomes in the list. You can see where we have tails, heads, 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 tails, heads, 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 tails, heads, and heads, 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 tails. So 4 outcomes in the sample space out of 16. and 4 out of 16 reduces down to 1 out of 4, or 0.25. So you have a 25% chance that exactly one of the 4 tosses is tails. Okay, the main point there is that you can see that when the sample space is listed out, it's a much easier question to answer. You'll see that with this example also. 2 dice are rolled. One is red and one is blue. There are 36 equally likely outcomes. They are ordered pairs in the form red, comma, blue. And you can see that I've listed all of those outcomes here. What is the probability that the sum of the dice is 5? Okay, so I'm looking at all of these numbers, these pairs of numbers, and I'm looking for sums of 5. And the very first sum of 5 that I can come across is this one right here. 1 and 4 have a sum of 5, or in this column it looks like 2 and 3 have a sum of 5, 3 and 2 in the next column, and it almost looks like we're going up this diagonal here, and then 4 and 1 in this column. Obviously, once we get into this column and the final column, we no longer have or no longer can achieve a sum of 5. So we have 36 total outcomes in the sample space. Applying that fundamental idea of probability, let's say, how many ways can our specific event occur where we get a sum of 5? Well, that event can occur 4 ways out of the 36. 4 divided by 36 can be reduced to 1/9, and 1/9 is equal to 0.1 repeating. You'd see if you put 1 divided by 9 in your calculator, you get 0.1111, and that goes on forever. So you get approximately 11%. You have approximate 11% probability that the sum of the 2 dice when they're rolled is 5. And the game of craps, that is another casino game, is one that is actually based upon the sum of 2 dice. And you might know that the most common sum that you can get when you roll 2 dice is actually 7. And again, that's kind of one of the cornerstones of the game craps. Okay, last example in this video. And this example contrasts your empirical probability with theoretical probability. So remember, most of the time when we talk about probability, we're going to be talking about it on a theoretical level. But sometimes we talk about probability just based upon the results of an experiment. So here it says a die is rolled 600 times. On 85 of those rolls, the die comes up 6. Use the empirical method to approximate the probability that the die comes up 6. So theoretically, now let's not talk empirically for a second, but theoretically, if you rolled a die 600 times, wouldn't the probability that the die come up 6, it'd just be 1 out of 6. I mean, you can get a 6 one way out of the 6 ways of rolling a die. So if you rolled a die 600 times, you'd probably expect about 100 6s or so. And 100 divided by 600 would lead you to 1/6. But when we conduct the experiment, that is not what happens. And so if we look at the experimental results, that probability is going to be a little bit different than a theoretical probability of, say, 1/6. So only 85 of the rolls produced a 6. So if you did an experiment 600 times and 85 of the times the die came up 6, then you would say empirically that 85 out of 600 would be the proportion of times that the die comes up 6, because that's the best thing that you have to go on. And 85 divided by 600, if we put that into the calculator, is right around 14%. So let's just say that this is approximately 0.14. And again, that contrasts with the theoretical probability of 1/6, and the theoretical probability, here I'll write this down, your theoretical of a die coming up 6 would be 1 divided by 6, and 1 divided by 6 is equal to 0.16, and the 6 repeats, and so almost 0.17. So 0.1666666, and it goes on forever. But you can see that there's a little bit of a discrepancy there. And that discrepancy is going to start to go away when the number of times that you simulate an experiment is much greater. And again, that just speaks to the fact that the law of large numbers suggests that our experimental probability will converge to our theoretical probability as the number of experiments gets very, very, very large. Okay, so this is it for the basics of probability. We'll talk about some specific aspects of probability and some formulas that you'll be applying in the very next video. So go ahead and check that one out now. Thanks.